This is the first series of lectures presented in my office at the University of Missouri, Kansas City, on the subject matter of Calculus 1. There will be approximately 12 tapes in this series, and each one of them will be in front of the blackboard here. They'll be presented in short episodes, and between the episodes, the picture will fade out. There'll be a slight pause, and the next episode will begin. The title of each episode will be given up here, and the number of the episode here. If the number is followed by an asterisk, this means that the particular episode is not necessary for the calculus, but is additional material. If the topic is followed by an asterisk, this means that an exercise is being done on that topic. Okay, let's begin. The first topic we will deal with is set theory. The idea of a set is basic to all of modern mathematics. A set is a collection of objects brought together in such a way so that given any object whatsoever, it either belongs or does not belong to the set. We'll usually be dealing with collections of numbers. However, one can deal with collections of any objects whatsoever. Sets are symbolized with capital letters, frequently the letters A, B, and C. And the elements of sets are usually symbolized with small letters, for example, A, B, and C, little a, B, and C. Sets are given in two ways, either by enumeration, that's to say listing the elements that belong to the set, or by description, that's to say describing the elements that are in the set. In either case, set brackets are used. These brackets look like this. And in the case of enumeration, the objects which are enumerated are put in between the brackets. For description, the description is put within the brackets. One can make these set brackets most easily by considering the left-hand bracket as being an S followed by a rounded 2, and the right-hand bracket as being a 2 followed by a rounded S. For example here, the first three counting numbers, or natural numbers, are the numbers 1, 2, and 3. And one would write the set of those numbers as the set 1, 2, and 3 using the set brackets. This is the set given by enumeration. If one wanted to give the set by description, one uses the same set brackets and writes the set of, let's say, X, where this is supposed to be a general element of the set. A line is used here, or sometimes a colon, such that X is a natural number. And X is less than 4. These are the same set. They have exactly the same elements, and so we write that one set is equal to the other set. If a little element A belongs to a set capital A, we write A belongs to A. This symbol here is a rounded epsilon and indicates that this element belongs to this particular set. If all the elements of a given set belong to a different set, for example, if all of the elements of A belongs to a set B, we write A is contained in B, where this is a U on its side. This is A is contained in B if whenever A is in A, then A is necessarily also in B. Thus, two sets are equal, A equals B if and only if, and I write IFF as abbreviation for if and only if, a set A is contained in a set B and B is contained in A. Okay, there are a couple of operations that are involved with sets. Particularly, these are called union and intersection. The union of two sets. We've got two sets A and B. A union B is the collection of all x such that x belongs to A or x belongs to B. Or both. The or here means one or the other or both. So this is the collection of all elements that are either in A or in B, or perhaps both. The intersection of two sets is the set of x such that x is in A and x is also in B. These are the intersection of two sets. This is a collection of all elements that the two sets have in common. Sometimes they don't have any in common, in which case there won't be any elements in this intersection, and we need frequently a particular set which is called the empty set. It's symbolized with the Greek letter phi. The empty set this is the set that doesn't have any elements whatsoever. Also, if we have two sets, frequently we want to consider the set of elements that are in A which are not in B. We write this as A remove B with a diagonal line like so. This is the set of x such that x is in A and x is not in B. And we can write is not in with the belong sign with a line through it. Union and intersection obey several rules. In particular, the order is not really important in the way in which union and intersection are done. That's to say that A union B is the same as B union A. It's exactly the same set, and the way to show this is to show that every element that belongs to the left-hand side here also belongs to the right-hand side. Thus, if x belongs to A union B, then it belongs to either A or B or both, and so consequently it belongs to either B or A or both. Similarly for intersection. A intersect B is the same set. It's equal to B intersect A. This is a sort of commutative law for union and one for intersection. A sort of associative law also holds. That's to say that A union B, or union A and B, and then union C, that's the same thing as you'd get if you took A and unioned it to what you got if you took B union C. Right? So that consequently these parentheses are really not necessary here. Likewise for intersection. A intersect B, intersected A and B, and then took the intersection of that with C. That's the same set that you would have if you took A and intersected it with what you got when you took B and intersected it with C. Again, the parentheses are not necessary because this associative law holds. Two additional laws which are somewhat interesting also hold. There's distributive laws, and they hold in both directions. That's to say, if we take A union B intersect C, and here the parentheses are necessary, this is the set A union B intersected with the set A union C. And the other direction also holds here. A intersected with B union C is the same set as A intersected with B union A intersected with C. Well, we will frequently be using sets that consist of numbers or of other mathematical objects. It's worthwhile noting that these sets can be used in general situations, and this notation will be quite useful for our purposes in calculus. Next topic we're going to be concerned with are numbers. Obviously, we're going to need numbers in calculus. The number systems are most basic to mathematics. There are several of them. And the counting numbers, or natural numbers, are the first of these. And these are symbolized with an N, with a rounded right-hand side. This is the set of numbers that consist of 1, 2, 3, 4, and so forth. These are numbers that are used in counting, and therefore they're natural numbers. Second system of numbers is that of the integers. These are symbolized with a Z with a line down the diagonal here of the Z. And these are the numbers 0, plus or minus 1, either plus or minus 1, plus or minus 2, plus or minus 3, and so forth. The reason for the Z is because of the addition of the 0 to the numbers here along with the negatives. All right. Third system of numbers which is used are the rational numbers. These are symbolized with a Q. And the rational numbers are all numbers of the form P over Q. All x such that x equals P over Q, where P is an integer and Q is a natural number. There's an equality relationship between these numbers P and P over Q. That's to say P over Q is equal to R over S if, again, if and only if PS equals RQ. Addition among these numbers is performed as usual. To say P over Q plus R over S is equal to, for a common denominator we have Q S, and in the numerator we have P S plus R Q. Multiplication is given by P over Q times R over S is equal to P times R over Q times S. Okay. Then the subtraction is clearly given with a negative sign in both of these places here. And division is done in the common, ordinary way of inverting the number to be divided and multiplying. Division is always possible, providing the number to be divided. The square to divide the number is not equal to 0. Right. But there are other numbers besides the rational numbers. In fact, it's well known, and we'll see shortly, that the square root of 2, for example, is not a rational number. And for our purposes, we need all of the numbers that would represent various distances. And these numbers are called the real numbers. And they're symbolized with capital letter R with a double line drawn on the left-hand side of the R. These are all numbers of the form a whole number, that's to say a natural number with plus or minus and or possibly 0, followed by a decimal point. And then now in the decimal system, x1, x2 is continuous, xk is continuous. That's to say they're all non-ending decimals. Here 0 is less than or equal to each xk is less than or equal to 9. All numbers that can be written with a plus or minus sign, a natural number, or 0 and 0s and 9s. Right. Again, addition, subtraction, multiplication, and division are possible for these numbers. And this expression for a number is not completely unique. That's to say, two numbers which end in 0s and 9s can be equal. For example, 4.2199999 is equal to what the number that you'd get if we were to look at 4.22 and follow this with all zeros. One can see this by subtracting these two numbers. If one were to subtract these two numbers, you're going to find out that you're going to have no difference whatsoever. We'll see that in just a moment. To add two numbers, you have got to proceed from the left rather than from the right. So that, for example, 4.3726 plus 3.6415 and so forth. Right? We would add here, we would add the 4 and the 3, getting 7. And since there's nothing to carry, we can write the 7 down. 6 and 3 is 9, but we've got 1 to carry here. Oops. That means that this is going to be a 10, and that this has to be an 8. 7 and 4 is 11, and there's nothing to carry from 2 plus 1. There isn't even any possibility of it. So we get 11. We can check now here that this is 11, 10, 8. 2 and 1 is 3, but we're going to have to carry from the 6 and 5, so it's going to be 4. And 6 and 5 is either going to be 11 or 12, depending upon what the next number is. And so we don't really know until we know more digits in the decimal expansion. So you can add these two numbers by proceeding from the left. Similarly with subtracting them. Likewise with multiplying and division. You multiply and divide by getting more and more decimal places of accuracy for the given answer. If we were to subtract this number here from this one, what's going to happen? We're going to have 4 minus 4 is 0. 2 minus 2 is 0. 2 minus 1 would normally be 1, but we have to borrow 1 here, so it's going to be 0. 0 minus 9, again, would be 1, except we have to borrow 1 from here, so it's going to be 0. And 0 minus 9, 0, and so forth here. So it's clear that if a number ends in repeating 9s, then the next number up here, so to speak, alphabetically, is equal to it. So say if we replace the 9s with 0s and we add the next digit up, like so. The difference between them is 0. Another way to see this is as follows. A third is clearly the number 0.33333 in decimal expression. And if we were to multiply that by 3, we're going to get 0.99999, and so forth. But 3 times a third is clearly equal to 1. So the number which ends in 9s is equal to the number which begins 1.000, and so forth. If a particular decimal terminates, it's understood without these three dots that means that zeros from then on are the number. So that, for example, 4.6 is equal to 4.60000. Now, clearly, we're not going to use all of the accuracy involved in here, but for the purposes of the theory of measurement and for the subject matter that we're going to deal with, you need to have all of the numbers that could possibly represent quantities, distances, lengths, and so forth. The numbers that we want are going to be those which are represented on the distances between 2 points on the line. And it was known to the Pythagoreans, it was their secret, but it's no secret anymore, that there are numbers which are not rational numbers. In particular, the number which is the square root of 2, and can be constructed as a length by drawing a triangle here with sides 1, and then the hypotenuse of that triangle is going to have for its length square root of 2. To see that the square root of 2 is not a rational number, we will show this proceeding with the assumption that it is, and showing that this is impossible. We suppose that the square root of 2 was some rational number, p over q. Then we could reduce this rational numbers to what's called lowest terms. That's to say, so that the numerator and denominator have no common factor. Right? In particular, the numerator, if the numerator is even, the denominator will not be even, because if 2 was a common factor of numerator and denominator, then you could factor it out and have this in lower terms than you did. Likewise, if the denominator is even, the numerator would not be even. Now, if the square root of 2 is equal to p over q, then 2 is p squared over q squared. So that 2q squared is p squared. And p squared is an even number, and so consequently p must be an even number. That is to say, p is 2 times some other number r. Now, if I substitute 2r in here for p, I find that 2q squared is 4r squared, or the q squared is 2r squared. This says that q squared is an even number, and consequently q must be an even number. So here we have that q is even, and back here we had that p must be even, but that's impossible, as we noted previously, because if p and q are both even, we could divide them by the number 2 and continue doing this until one of them was odd. And so this is a contradiction. Sometimes one writes a contradiction by drawing a circle with an x through it. Right? Can't happen. And so consequently the square root of 2, which is the distance, is not a rational number. Right? What we want are all of the points on the line. And these are placed on here as follows. 0 is put in a particular position, and 1 to the right of it usually. And then the numbers, the whole numbers, are placed on the line, the natural numbers to the right, 1, 2, 3, 4, and so forth, with the same distance between them. And to the left, -1, -2, -3, and so forth here. And then between 0 and 1, the halves are positioned. 1/2, 3/2, 5/2, 7/2, -1/2, minus 3 halves, minus 5 halves. The thirds can be positioned then between these, a third and 2/3. All right, 3/3, 4/3, and so forth here. And all irrational numbers can be placed on the line. And these are so close together that it's tempting at first to believe that they would have been all of the numbers, but it's clear from this over here that they're not. To get all the numbers on the line, what we need are the real numbers, and these being the non-ending decimal expansions, we can see how these correspond exactly to the points on the line. That's to say, if we're given a point on the line, it's, let's say, between 2 and 3. Our point is. So we can write a real number corresponding to this, beginning with 2. Right. If we now take the interval between 2 and 3 and divide it up into 10 parts, and we find that it is in the 6th part here, then the number is going to be 2.6. We can now take the interval here and divide it into 10 parts. And theoretically, at least, we can determine which part it belongs to. It maybe belongs to the second part, in which case the number is 2.62. Dividing that part into 10 parts, we might find it's in the 7th, and so forth here. Thus, a point on the line, being an exact position on the line, gives rise to an infinite decimal expansion here. A whole number followed by a non-ending sequence of numbers between 0 and 9. Conversely, suppose that we had a number like this. 3, let's say, 0.75924, and so forth. Well, I'm working only with positive numbers here, but it could clearly do the same thing if the number was negative. This number begins with 3.7. It's got to be somewhere between 3 and 4. So the number is going to be in here somewhere. It's 3.7, so if we proceed 7 divisions over here to the right, we find that the number has to be somewhere in here. Right. 3.75, if we divide this up into 5, we find that the number has to be in the 5th position here. And similarly, dividing that into 9, and the intersection of these intervals here is going to consist of a single point, and that's going to be the point that corresponds to this real number. So each point on the line is a real number that corresponds to it, and each real number, there's a point on the line that corresponds to it. There's something worthwhile noting besides this. That is that a real number is a rational number if and only if the digits in the decimal expansion repeat in blocks. We can see this by a couple of examples. First of all, let's suppose that the digits repeat in blocks. Let's suppose that we're dealing with, for example, 3.267, 67, 67, and from now on these are all 6 sevens. Let's call this number x. Now, since it repeats in blocks of 2, let's multiply this number by 100. If it repeated in blocks of 3, we multiply by 1,000. Blocks of n by 10 to the n. So we get 100x is equal to 326.7676767, and so forth. By multiplying by 100, we've caused the 6 sevens to line up above each other here in 100x. So that consequently, if we subtract these two, we're going to get that 99x is equals to, what do we have here? 323.5, and all the 6 sevens will cancel out here. That's to say that x is equal to 323.5 divided by 99, or 3,235 over 990. So we've shown that the number is the rational number 3235 over 990. Conversely, if we start with a rational number, we will find that its decimal expansion repeats in blocks. For example, let's take the number, let's say 6/7. This will illustrate things. If we divide 7 into 6.00000, what happens here? Well, we get 7 into 60, is 8 times. 8 times 7 is 56, with a remainder of 4. Well, we started out with 60, now we're going to be looking at 40. Well, there are only so many possible remainders that we're going to run through, and all of them will be less than 7. Since there are only 6 of these remainders less than 7, eventually they're going to have to repeat. 7 into 40, for example, is 5. 5 times 7 is 35. Subtracting here, we get 50. 7 into 50 is 7. We get 49. Subtracting, we get 1. 7 into 10, write it up here, is 1. 1 times 7 is 7, and subtracting we get 3. 7 into 30 is 4. 4 times 7 is 28. Subtracting we get 2. 7 into 20 is 2. Subtracting we get 2 times 7 is 14. And subtracting we get 6 again. We're back to the beginning. At some point we would have had to be back to the beginning. At any rate, this shows that the number 6/7 is equal to 0.857142, and then this repeats, 857412. It's clear that any other ratio like this would have the same properties. So that a rational number, consequently, has a repeating decimal expansion, and a number has a repeating decimal expansion if and only if it's a rational number. So that consequently, one can give a lot of examples of numbers which are not rational. For example, a frequently given number is 0.01, 001, then 3 zeros and a 1, and 4 zeros and a 1, and so forth. It's clear that this does not repeat in any blocks, and so consequently it cannot be a rational number. Right. We want a description of the natural numbers which gives all of their properties, and begin with what are called the field axioms. That is to say, being real numbers are a field. A field is a set, say F, with two operations. Addition, plus, and multiplication, written with a dot frequently. An operation is something that takes elements from a given set back into the set itself. Along with the two operations, there are 11 axioms that these operations have to satisfy. However, they are easily organized into a neat pattern, and I'm going to do that right now. Okay. So, for addition, and for multiplication. First of all, what we have is called closure. That's to say, for each A and B in F, A plus B is defined and it's an element in F. And likewise, we have closure under multiplication. A times B is in F. So this is for every A, B, and C. All these statements are for every A, B, C in F. The closure. Secondly, the associative law holds. Associative law says that A plus B plus C is equal to A plus B plus C. This is the associative law for addition. That's to say, if you take A and add it to B and add that to C, you get the same thing as if you take A and add it to B and then add it to what you have if you take B and add it to C. Likewise for multiplication. A times B times C is equal to A times B times C. The associative law. There are identity elements. The identity for addition is a 0. So there is a 0. So that A plus 0 is always equal to A. And for multiplication, there is a 1. So that A times 1 is always equal to A. For each A, again, in F. All right. Now, defined in terms of the identity elements are inverses. For each A, there is a negative A. So that A plus negative A is the 0 element. And for each A, except for 0, there is an A inverse with respect to multiplication, or the reciprocal of A, so that A times A inverse is equal to 1. We have also what's called the commutative law. That's to say, for addition, A plus B is always equal to B plus A. And for multiplication, A times B is equal to B times A. So here what we have are 10 rules, 5 for addition and 5 similar ones for multiplication. Let me mention here that there is a 1, so that A times 1 is equal to A, and it's also supposed that the 1 is not the same as the 0 element. So it has to be an additional element besides the 0 element. Right. At this point we have these 10 rules. The 11th rule is called the distributive law. It's the rule that relates addition to multiplication. And it says that A times B plus C is equal to A times B plus A times C. You're perhaps familiar with the fact that we don't always write the dot here when it's clear what's meant. Likewise, due to the commutative law and the associative law together, if things are being added, it's not necessary to write parentheses A plus B plus C. These parentheses can be dropped. Same thing with if 3 quantities are being multiplied or more quantities are being multiplied, the parentheses can be omitted. Examples of the field are the rational numbers and the real numbers, but there are others. And so we are not to the point of describing all of the rules that we want for the real numbers. What we wish to have here is a complete list of axioms so that if something behaves like the real numbers, then it's going to satisfy those axioms, and vice versa. Something that satisfies those axioms can be treated as the real numbers. Here, though, are the first 11 axioms, those involved with the field. We're going to look at several examples of fields. Two that stand out, of course, are the rational numbers Q and the real numbers R. But there are quite a few others. The rational numbers and real numbers can clearly be checked to satisfy all the 11 axioms for a field. However, let's consider a very small field. The field is going to consist of only a 0 element and a 1 element. Now these are not your standard 0 and 1 elements, but I'm going to give the additions table for these elements. 0 and 0 is 0, 0 and 1 is 1, 1 and 0 is 1, and 1 and 1 goes back to 0. This is addition modulo 2. That's to say, when you get to 2, you go back to 0 again. The multiplication table looks like this. 1 and 0. 1 and 0. 1 times 1 is, 0 and 1. 0 and 1. 0 times 0 is 0. 0 times 1 is 0. 0 times 1 is 0. And 1 times 1 is 1. Okay. You can check that this addition and this multiplication for these numbers satisfies all 11 field axioms. And so consequently that this is a field. Right? This is the field of addition and multiplication modulo 2. Well, there are others. For example here, if we took the numbers 0, 1, and 2, we can make out an addition table for them. This is going to be addition modulo 3. That's to say, if we get to 3, we go start back over with 0. 0, 1, and 2. 1, 2, and 0. 2 and 0 is going to be 2. 2 and 1 is going to be 0. And 2 and 2 is going to be 1. Right? Multiplication would look like this. 0, 1, and 2. 0, 1, and 2. 0 times 0 is 0. Times 1 is 0. 0 times 2 is 0. 1 times 0 is 0. 1 times 1 is 1. 1 times 2 is 2. times 0 is 0, 2 times 1 is 2, and 2 times 2 is 1. So it's clear that 2 is its own multiplicative inverse here. 2 times 2 is what you have when you look for the multiplicative inverse of 2. Right? It's going to be 2. 2 times 2 is 1. Okay. So here's an example of a field. You can check that this addition and this multiplication here satisfy all the field axioms. Here's an example of a field. The rational numbers are a field. The real numbers are a field, but there are more. The complex numbers. The complex numbers are all the numbers of the form a plus bi, where a and b are real numbers, and I here behaves like as if it was the square root of a minus 1. That's to say, when you square I, you get minus 1. Yeah, it's not too difficult to show that these numbers are closed under addition, subtraction, multiplication, and division. That's to say that there's a 0 here and a 1, and you have inverses and associative law and so forth, and so this is a field. There are additional fields. Let me give one more example. The collection of all P of x divided by Q of x, where P of x and Q of x are polynomials. And Q of x is not 0. That's to say, it's not the 0 polynomial. Then you can show that you have addition, subtraction, multiplication, and division here. These result in functions which are perhaps not defined at a finite number of points, but that's no great problem. We don't worry about those points and just concern ourselves with the points where the function is defined, and these are functions. This is closed under addition, subtraction, multiplication, and division. There are naturally then a 0 element, a 1 element here. The 1 element is the polynomial 1, and all of the field axioms are satisfied. So this is an example of an additional field. So we have quite a few here at this point. Actually, if we take addition and multiplication modulo a prime number, the resulting table will be a table for a field. So if for each prime number we have got a field, rational numbers, real numbers, complex numbers, ratios of polynomials, all of these are fields. We're going to need some additional axioms to get at the field that we're going to be basically interested in, namely the real numbers, to eliminate these additional fields from the picture. The real numbers, as well as the rational numbers, are an example of unordered fields. Several of the other fields cannot be ordered, and we're going to want to talk about ordered fields and the axioms which give you order on a field, or even on a set, and real numbers then will be an ordered field. Along with the axioms for order, there will be one more which will exactly delineate the real numbers when added to the previous axioms. It's called the completeness axiom. First, let's look at order on a field. The easiest way to get at this, perhaps, is a sort of a grade school approach. That is to say, a field will be said to be ordered if there is a set P, the positive elements contained in the field F, so that three things happen. One, if A and B are in P, then A plus B is also in P. Whenever you have two positive elements, then their sum is also positive. Secondly, if A and B are in P, then the product of A and B is in P. The product of two positive elements is positive. Right. Thirdly, one of three things must happen. Either A is in P, or A is equal to 0, or the negative A of A is in P. Exactly one half holds. Right. If we have all three of these, and you're probably no doubt familiar with the fact that these hold for the rational numbers, for example, and also the real numbers, then we can define an order on the field as follows. We say that A is less than B if B minus A is in P. For convenience, we also want several other ways of writing the same type of thing. We want A to be less than or equal to B if A is less than B or A is equal to B. And we want to write A greater than B if B is less than A, and A greater than or equal to B if B is less than or equal to A. This is for convenience, so that you can write these in whichever order is convenience. Okay, so here starting with positive elements. If you can find a set of positive elements which are closed under addition and multiplication, and so that exactly one of these three holds, then you can define an order on the field. Right. The order on the real numbers or the rational numbers is the natural one involving the positive elements. There's another approach that you can take, though. You can define an order on a set. Right. And for that purpose, we will use the less than or equal symbol here to define an order on a set. Right. Given a set S, right, an order on S is less than or equals to satisfying. And now here we're going to have, this is the easiest way, we're going to have several more assumptions here before we get to an order on a field if we just start with an order on a set. One, A must always be less than or equals to A. Two, if A is less than or equal to B, and B is less than or equal to A, then A equals B. That's to say, if A is less than or equal to B and B less than or equal to A, then A and B are the same element. Thirdly, if A is less than or equals to B, and B is less than or equals to C, then A must be less than or equals to C. We need these three rules. We also need another one. These three rules do not guarantee that any two elements from the set S be comparable to each other. That's to say that either one be less than the other or vice versa. So we need to assert that. Right? Either one of the following three holds. Exactly one holds. Exactly one of A is less than B, A is equal to B, and B is less than A holds. That's clearly comparable to this one over here. Now, this is an order on a set. Right? You can think of an element as being to the right of another element if it's larger than the other elements. And clearly we can define this right here too. These two here at any rate. A would be less than B if it's less than or equal but not equal, and then these two are defined in terms of the other. All right? Now, given that we've got that, we want an order on a field, and this means that we want to have the order to be consistent with addition and multiplication of the field. So we're going to need some additional axioms here. And order on a field also satisfies these three. If A is less than B and C is any element, then A plus C is less than B plus C. Or we could also write this as A is less than or equal to B, then A plus C is less than or equal to B plus C. So this connects the order with addition. Secondly, if A is less than or equal to B and C is greater than 0, then A times C is less than or equal to B times C. Thirdly, if A is less than or equal to B and C is less than 0, then the inequality is reversed. The order on the inequality is reversed. A times C is greater than or equal to B times C. These two tie the inequality with multiplication. Now, if you've got an order on a set that's also an order on a field, then you can define a set of positive elements. P to be equal to the collection of X such that X is greater than 0. And then in this set P will satisfy these three over here, so that it will define an order on a field. Okay, so that if you start with an order on a set, it's also an order on a field, you can then get a collection of positive elements. If you start with a collection of positive elements, you can then get an order by defining A less than B. Here we define P as the set of X, which is X greater than 0. Here we define A less than B. And so either of these two here will do to define an order on a field. And the field is an ordered field, then if there's an order on it. These, along with one more axiom, will delineate the real numbers, the rational numbers, along with the real numbers, and there are even some additional fields that satisfy the fact that they are ordered. The final axiom that's needed to describe the real numbers is called completeness. Now this is sometimes not used in calculus texts, and it's sort of slided over, but it's really needed in order to do things correctly. The number line doesn't have any gaps in it. That's to say, unlike the rational numbers, it's not possible to divide the line into two sets A and B, so that A and B are not empty, and A has no largest element, and B has no smallest element. It's possible to do this with the rational numbers. For example, the rational number is less than the square root of 2, and the rational number is larger than the square root of 2. We want a real line with no gaps. Now, let's talk about completeness for an ordered set. All right. For an ordered set, We're going to say that if A is contained in S, that B is an upper bound for A if, when any element A is chosen from A, then A is less than or equal to B. The element B may belong to S, but it doesn't have to. What it has to do is it has to be larger than or equal to every element in A. In that case, it's called an upper bound for the set A. All right? If A again is contained in S, B is said to be a least upper bound for A if B is an upper bound and there are no smaller upper bounds. If B prime is an upper bound, and if B prime is an upper bound, then B is less than or equal to B prime. Right? That's what's meant by a least upper bound. Okay, so here we have an upper bound, and here we have a least upper bound, and now finally the completeness axiom. S is said to be complete if each not-empty set A contained in S, which has an upper bound, also has a least upper bound. That's the definition then of complete. Set S, ordered set, is complete if each non-empty set which has an upper bound also has a least upper bound. Now, one frequently writes for set A contained in S, L period U period B of A, or more frequently, sup, S-U-P of A. This stands for the word supremum. Okay, now the supposition is that the real numbers are a complete ordered field. Any complete ordered field also behaves exactly like the real numbers. Give you a rough reason why. The completeness axiom guarantees that there can be no gaps. If we have got A that's not empty and B that's not empty, then either A has a largest element or B must have a smallest element. Right? There cannot be any gaps. If every element in A is less than or equal to B, then there must be a largest one in A or a smallest one in B, and that follows from this. All right? So now what that means is we're going to be able to measure anything that we wish to using the real numbers. Okay. The reason why this exactly describes the real numbers is as follows. If we take any ordered field Right? If it's also a completely ordered field, then we can take it, if we've got a second completely ordered field, we can compare them by relating the zero element in the one field to the zero in the other, the 1 to the 1, the 2 to the 2, the rational numbers to the rational numbers, and the least upper bound of a given set of numbers in the one to the least upper bound in the other, and we'll find that they have exactly the same shape, so to speak, the same elements, and that this comparison gives us the same thing with respect to addition, subtraction, multiplication, division, and order. So completeness is exactly the thing that you want for an ordered field to make sure that it looks exactly like the real numbers. That is to say, the real numbers are a complete ordered field. And any complete ordered field looks exactly like the real numbers. Certain subsets of the real numbers occur frequently as collection of solutions to certain problems, and these are called intervals. We write the real numbers as R here, and a given collection of numbers between two numbers, here A and B, right, can be written, if we want the ones that are strictly between A and B, this is written as A comma B with rounded parentheses around it, and read the open interval AB. It's equal to the set of X such that A is less than X is less than B. The open interval. If we wish to include the A and the B, then what we end up with is what's called a closed interval. And we use square parentheses for that. This is the collection of X such that A is less than or equals to X is less than or equals to B. One frequently will draw the open interval with a rounded parentheses up here like so. Some books will draw this with a little empty circle between them. That's to say, an empty circle here and an empty circle here and a line connecting them. The closed interval can be represented like this, schematically. Yeah? Then there are a couple of possible half open intervals. They're always called half open intervals, never half closed intervals. Right? We could include B, but exclude A, like so. So that the square bracket means the B is included, the rounded bracket means it's excluded. The set of X such that A is less than X is less than or equals to B. Or A included and B excluded, the set of X such that A is less than or equal to X is less than B. We also consider intervals which go on indefinitely as follows here. The interval A, and then we use the symbol an 8 on its side, read infinity. This is not, however, meant to be in any way mysterious. There's no number infinity on the line, and if you write this out as the set of X such that X is larger than A, you see that there's nothing mysterious about it at all. There's no infinity here. This is just a convenient notation, and that's going to hold true in all the rest of mathematics. Whenever the symbol infinity is used, it does not represent anything mysterious or mystifying. It simply indicates that something without n is occurring here, and the symbol can always be removed and the quantities rewritten without the symbol involved and without much mystery. At any rate, this is the open interval from a to infinity. The rounded parentheses is used at the infinity because there is no such number. The closed interval a to infinity, the set of x such that x is greater than or equal to a. And we also use the intervals from minus infinity to, let's say, b. Here, always excluding the minus infinity, there's no such number, and including b here. And this is going to be equal to the set of x such that x is less than b. And last possibility here, I guess, is minus infinity to b, including the b. This is the set of x such that x is less than or equal to b. One can write the real numbers themselves as the interval minus infinity to infinity. Okay, so schematically, one could clearly represent these as, for example, for the closed interval from a to infinity, like so. Or for the open interval, like so. And you'll see sometimes this also, the open interval, and this for the closed interval. Okay. These intervals are just slightly shorter than the set notation that would be needed to describe them, and they are frequently given as solutions, let's say, to inequalities or to other mathematical problems. We're going to begin several episodes here that deal with inequalities. An inequality is sort of like an equation. A linear inequality is one of the form ax plus b is less than or equal to or greater than or greater than or equal to or less than cx plus b. If this was an equal sign here, then this would be a linear equation. So these are linear. These are the easiest to deal with. And one simply has to be aware of the fact that, okay, you can add or subtract any quantity to both sides of an equation or an inequality, but if you multiply an inequality by a positive number, it remains the same, but it is reversed if you multiply it by a negative number. So that, for example, 7x plus 6 is less than or equal to 3x plus 2. Right? The way to solve this is the same way in which you would solve an equation. That's to say, bring the x's to one side and the numbers to the other. So that, for example, if we subtract 2 from both sides here, we get 4, less than or equal to 2. If we add 7x to both sides here, or subtract 7x, from both sides here, we get minus 4x. Now you'd like to divide both sides by minus 4, but you have to be careful here, of course, because minus 4 is negative. We're multiplying by minus a quarter, essentially, and so we have to reverse the direction of the inequalities. That's to say, we get x is less than or equal to minus 1. Or the solution set, the set of all x for which the given inequality holds, is minus infinity to minus 1. And here the minus 1 is included because we've got equals minus 1 as a possibility. All right. So for linear inequalities, you proceed just exactly as you would with a linear equation, being careful, though, that if you ever multiply by a negative number, the inequality is reversed. Inequalities are tricky, and they show up quite a bit in calculus, and so it's worthwhile learning how to deal with them. Let me show you a way not to deal with them. Let's suppose we have the inequality 1 over x. Is larger than 5. Right? Well, the thing that you're tempted to do with this is to multiply both sides by x and get what is larger than 5x. Let me change this. Let me change this to 1 over x is less than 5. And then again, it's tempting to multiply by x and get what is less than 5x, and then divide both sides by 5 and get x is larger than a fifth, or 1/5 is less than x. But this is not right. All right? Because sure, all the numbers larger than a fifth satisfy 1 over x is less than 5, but there are others. For example, the negative numbers. Any negative number, for example, -1, 1 over -1 is less than 5. And we didn't get the solution set to this inequality using this method right here. And that's because this is a bad method. What did we do wrong? We multiplied both sides by x. When x was an unknown quantity, it was not known whether it was positive or negative. So we don't really know that this should go in this direction right here. So this is wrong. How can you handle this? Well, you can handle this the way you can handle a number of other inequalities. You can consider several cases or possibilities. 1 over x less than 5. Well, what you want to do here is to multiply both sides of this by x. But that's not legitimate because you don't know whether x is positive or negative. If you consider two cases, though, one is the case where x is greater than or equal to 0, and the other is the case where x is less than 0. Right? That's to say, the right-hand case here consists of the numbers that are in the closed interval 0 to infinity. Open at infinity, huh? And these consist of the numbers that are in the interval minus infinity to 0. We consider these two different intervals here, and we work with them differently. So that, for example, if x is greater than or equal to 0, then we can multiply both sides of this inequality by x, and we will get 1 is less than 5x, or dividing both by 5, which again is legitimate, x is larger than 1/5. So what this says is that among the numbers in 0 to infinity, the ones which are larger than a fifth are the solution set, are part of the solution set for this inequality. That's to say, the numbers from 1/5 to infinity those numbers in here, which are larger than a fifth, are part of the solution set. Now we need to consider the remaining numbers, the ones from minus infinity to 0. Right? Well, if the number is between minus infinity and 0, x is less than 0, and so if we multiply by x, we've got to reverse the direction of the inequality. That's to say, multiplying in this case over here by these numbers x, we have 1 is larger than 5x, or x is less than a fifth. And the numbers between minus infinity to 0, which are less than a fifth, are all of the numbers between minus infinity to 0. So we get minus infinity to 0 as this part of the solution set. The entire solution set, then, is minus infinity to 0 along with the set 1/5 to infinity. So by considering two cases, namely the ones where x is less than 0 and the ones where x is greater than or equal to 0, we are able to work with this inequality. So let's do another example of the same type. Let's suppose that, let's say, 3 over x plus 2 is larger than or equal to 4, and we wish to find out which numbers this holds. Okay? Here what you would like to do is you'd like to multiply both sides by x plus 2, but this is not legitimate because you do not know whether x plus 2 is positive or negative. So we consider two cases. Here we consider the case where x plus 2 is greater than 0, and the case where x plus 2 is less than 0. Here one can remove the possibility of x plus 2 being equal to 0 because in that case this inequality doesn't make any sense. Okay, what? X plus 2 greater than 0. Well, these are the numbers where x is larger than minus 2, or in short, the interval from minus 2 to infinity. This other case here are the remaining numbers. That's to say, when x is less than minus 2, or the interval from minus infinity to minus 2. And we'll work with the numbers in this case here separately from this. Right? Now, if the number is in here, then x plus 2 is greater than 0, and so you can multiply both sides of the inequality by x plus 2. For example, 3 must be greater than or equal to 4 times x plus 2. Or 3 must be greater than or equal to 4x plus 8. Now subtracting 8 from both sides, we get minus 5 is greater than or equal to 4x. Or x is less than or equal here to 2 minus 5/4. Right? So the numbers between minus 2 and infinity, which are less than or equal to minus 5/4, are part of the solution set. Those are, in particular, the numbers from minus 2 to minus 5/4. Open on both sides here. No, not open on both sides. The 5/4 is included in the inequality here, huh? So closed at 5/4 and open at minus 2. Over here then, if we look just now, we now consider the numbers between minus infinity and minus 2, the numbers less than minus 2. Those are the numbers for which x plus 2 is less than 0. Right? If we multiply now both sides by x plus 2, we have got to reverse the inequality. So we get 3 is less than or equal to 4 times x plus 2. Or 3 is less than or equal to 4x plus 8. That is, minus 5 is less than or equal to 4x, or x is greater than or equal to minus 5/4. The numbers which are less than minus 2, which are greater than or equal to minus 5/4, there aren't any, huh? So that the entire solution set is given by this collection of numbers over here. If one had a more complicated inequality, one could proceed by using additional cases and solve it. We will do one of those next. All right, let's consider a more complicated one. Let's say 3 over x plus 1. When is that greater than 4 over x plus 2? Right? Well, here you'd like to multiply by x plus 1. You'd also like to multiply by x plus 2. Both of those are not legitimate because these are unknown quantities. So let's consider two cases first of all. X plus 1 greater than 0, and x plus 1 less than 0. Right? Now let's take each of those two cases and divide them into additional cases. X plus 2 greater than 0, and x plus 2 less than 0. We don't have to consider equal to 0 because this is not defined in that case. Likewise here, x plus 2 greater than 0, and x plus 2 less than 0. Okay, well these are the numbers where x is greater than minus 1. Right? And these are the numbers here where x is greater than minus 2. Well, if it's going to be in this case here, it's going to have to be greater than minus 1 and also greater than minus 2. That's to say, it's going to have to be greater than minus 1. So this case here consists of the numbers from minus 1 to infinity. Right? Here are these numbers, x is greater than minus 1 and less than minus 2. There are no numbers which are greater than minus 1 and less than minus 2, so there's nothing really in this case right here. That's to say, we don't need to consider it. These numbers here are the numbers when x is less than minus 1 and x is greater than minus 2. That's to say, these are the numbers from minus 2 to minus 1. Finally, these numbers here are the numbers where x is less than minus 1 and less than minus 2. That's to say, the numbers where x is less than minus 2 or minus infinity to minus 2. Now we've divided up the line into three parts here. Minus infinity to minus 2, minus 2 to minus 1, and minus 1 to infinity. We've excluded minus 2, and we've excluded minus 1. We're going to consider these three cases then. Right? If x plus 2 is larger than 0, and x plus 1 is larger than 0, then when we multiply both sides by x plus 1 and x plus 2, the inequality doesn't change at all, so that we get 3x plus 6 larger than 4x plus 4. Or, subtracting 3x from both sides, x less than 2. So the numbers in this interval which are less than 2 are part of the solution set. That's to say, the numbers from minus 1 to 2, excluding this 2 and excluding the minus 1. You get nothing here. So this adds nothing to the solution set. Over here, the numbers in this interval here, for those numbers, x plus 1 is less than 0 and x plus 2 is greater than 0. So if we multiply both sides of the inequality by x plus 1, it will reverse the inequality, and by x plus 2, it will then leave that inequality reversed. So we're going to get 3x plus 6 is less than 4x plus 4. Or again, subtracting 3x from both sides, we get x larger than 2. That's to say, the numbers in this interval here, which are larger than 2, are part of the solution set. Well, there aren't any. So that we get no new numbers from this interval in the solution set. No numbers in this interval at all are in the solution set. Finally, over here, when x plus 2 is less than 0 and x plus 1 is less than 0, then when we multiply it by x plus 2, it will reverse the inequality, and by x plus 1, it will reverse it back, and we will get the inequality 3x plus 6 larger than 4x plus 4. That's to say, again, x less than 2. The numbers in this interval which are less than 2 are all the numbers from minus infinity to minus 2. All of them are less than 2 in short. So this is part of the solution set. So the entire solution set are the numbers from minus infinity to minus 2, along with the numbers from minus 1 to 2. Okay. Proceeding by cases, you can determine what the solution set is, and it's necessary to do something like this because you can't multiply both sides of an inequality by an unknown quantity. another type of inequality which occurs is called a quadratic inequality. And that's an inequality that can be written in the following form. Ax squared plus bx plus c, and then an inequality sign, let's say greater than or equals to, or any of the other three, greater than or equal to 0. Right? This is a quadratic inequality, and the way to solve it is to note, first of all, the following, that if ax squared plus bx plus c equals 0, then the quadratic formula is x is equal to, that this occurs when x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. Okay? This is an important formula that should be memorized so that if you've got a quadratic equation, you can immediately solve it. What happens here? Well, there's three possibilities. One is b squared minus 4ac may be negative, in which case there are no solutions x to this. What this means is that this quadratic equation, which you probably know has a graph of a parabola, is a parabola which either opens upward or downward, but it never crosses the line y equals 0. Consequently, the solution to this equation, if b squared minus 4ac is negative, is going to be all the real numbers, here in this case, if a is positive. If a is positive, you'll have all the real numbers. If a is negative, you'll have none of the real numbers for the greater than or equals to case here. If it was the other way around, less than or equals to, then if a was positive, you would have no solutions to this. The empty set would be the solution set. And if a was negative, you would have all the real numbers for the solution sets. If b squared minus 4ac is equal to 0, then this is a perfect square here and can be factored as a perfect square. And if b squared minus 4ac is greater than 0, then this quantity here can be factored. The thing to do is to factor it. And so what you wish to do with this is to get it into factored form as one means of solving the quadratic inequality. So let's suppose that we have done that, for example, and that we have x minus 2 times 3x minus 4. We want to know when is this greater than 0. Right? There are a couple of ways in which one can approach this. One is that this is an equation of a parabola opening upward, and it's equal to 0 when x is equal to 2. And it's also equal to 0 when x is equal to, what? When 3x minus 4 is 0, that's to say when x is equal to 4/3. Since it opens upward, and it's 0 at 2 4/3, it must be positive, greater than 0, on 2 to infinity, to the right of 2, and it must also be positive to the left of minus 4/3, or between minus infinity and minus 4/3. One can use logic to solve this as well. Right? And that is, one can note that the product of these two numbers is going to be positive only in two cases. One case is when both numbers are positive, and the other case is when both numbers are negative. Right? So we have then two cases. One is when x minus 2 is greater than 0 and 3x minus 4 is greater than 0. That's to say when x is larger than 2 and 3x is larger than 4, or x is larger than 4/3. And in order for x to be larger than 2 and also to be larger than 4/3, x must be larger than 2. And we get this interval. The other possibility then is that x minus 2 be negative and 3x minus 4 be negative. Right? And in that case, we have what? X is less than 2, or 3x is less than 4, x is less than 4/3. X is going to be less than 2 and less than 4/3 when it's less than 4/3. This should have been 4/3 here. When it's less than 4/3, that's to say on the interval from -infinity to 4/3. So by considering the two cases, one where both are positive and one where both are negative, we get the solution set here. The same consideration with positive and negative can be done in the case when we've got a quotient. If we had x minus 2 divided by 3x minus 4, we wanted to know when that was greater than 0, we could consider two cases. One case would be when both of these were positive, and the other case would be when one was negative and the other one was also negative. If we had the inequality reversed and we wanted to know when this was less than 0, then that's going to be when one is positive and the other one is negative, or when the numerator is, for example, negative and the denominator is positive. More complicated quotients could be considered in the same way, likewise with more complicated products. For example, if we had x minus 2 times x plus 1 times x 3x plus 4, and we wanted to know when, let's say, this was less than 0. Right? There are several possibilities here for this to be less than 0. This could be positive, this positive, and this negative, or this could be positive, and this negative, and this positive, or this could be negative, and this positive, and this positive, or the final case, all three of them could be negative. If you consider all of these cases and find out the solution set for when this is positive, and this is negative, likewise with the others, and you union them up, this will give you the solution set for this inequality. Okay. We're still considering inequalities here, but we're going to now consider something which occurs frequently within mathematics because it's used in representing distances and things of that nature, and that is absolute values. The idea of the absolute value of a number is really a very simple one, and can be taught to a young child very easily, and elusive thinks that it's going to be that simple. For example, the absolute value of 2 is 2, the absolute value of minus 3 is 3, the absolute value of minus 5 is 5, the absolute value of 7 is 7. So the absolute value of a number is what you get, if you like, if you drop the sign from the number. Right? But the logic involved with this and needed to work with absolute values is considerably more complicated. The definition of the absolute value of the number x is that absolute x is equal to x if x is greater than or equal to 0, but it's equal to minus x if x is less than 0. Right? This seems tricky at first. Certainly if x is greater than 0, then the absolute value of x is x itself. And if it's negative, then the absolute value of x is the negative of that x, which is the positive number. Right? But when you're dealing with the absolute value of some quantity, it's more complicated, then you have got to be careful and realize that this is the definition. Okay. Now there are several simple inequalities involving absolute values that are generally taught in high school. And they're generally taught as the solution to all problems, and they're not really the solution to all problems. But let's look at them first. Right? If a is a fixed number greater than 0, then absolute x is less than a when what? X is between a and minus a. Right? That's really very apparent. That's one principle. A second principle, again, for a number x greater than 0 is that if a is number a greater than 0, that if a is greater than 0, then absolute x is greater than a when either x is greater than a or x is less than minus a. And if you replace this with less than or equal to, it replaces this with less than or equal to. Similarly here. If you replace this with greater than or equals to, these become replaced with greater than or equal to and less than or equals to. Okay, so what this will do is it will allow you to solve simple inequalities where you have a fixed number over on this side here. For example, absolute x minus 2. If we want to know when this is less than 7, it's going to be less than 7 when x minus 2 is less than 7 and greater than minus 7. Here, when you write a string of inequalities like this, you mean that this holds and this one also holds at the same time for x. And for such a string of inequalities, we can add 2 throughout, and we get minus 5 less than x less than 9. And so we find the solution set immediately is minus 5 to 9. And we can do this because the quantity over on the right side here was a fixed, definite number. Right. Another example. Absolute 3x minus 5. When is it larger than 2? Well, this is a fixed number over here, so this will be larger than 2 in two cases. One is when 3x minus 5 is larger than 2, and the other one is when 3x minus 5 is less than minus 2. Okay? This case holds adding 5 when 3x is larger than 2, or when x is larger than 2/3, or from 2/3 to infinity. That's part of the solution set. This case here holds, again, adding 5 when 3x is less than 3, or when x is less than 1, or from minus infinity to 1. Let's check this here. Adding 5, we have 3x less than 3, or minus x less than 1, minus infinity to 1. Here adding, we have 3x minus 5 larger than 2, 3x larger than, well, adding 5, 7, or x larger than 7/3, so this should be 7/3 to infinity. Okay. Now, granting that everything has been done properly, these two intervals here, the union of them is the solution set to the inequality when is absolute 3x minus 5 larger than 2. Okay, so in either of these two simple cases here, one can solve an absolute value inequality, an inequality involving absolute values by using the two simple principles. Okay. We're next going to look at some more complicated inequalities involving absolute values that show that you have got to be careful. Let's consider some more complicated inequalities involving absolute values. Not too complicated to begin with here. Let's consider, for example, when is absolute x, say minus 4, less than 2x? Right? Now here we've got absolute values, but this is not a fixed quantity over here. Now there are a couple of ways in which one can deal with this, but perhaps the simplest is to consider two cases. Right? We would really like to not see this absolute value up here, and we can remove it if we consider two cases. One is where x minus 4 is greater than or equal to 0, and the other one is where x minus 4 is less than 0. Right? If x minus 4 is greater than or equal to 0, that's to say if we're dealing with the interval, what? When x is greater than or equal to 4, or from 4 to infinity, right? And over here we're dealing with the remaining interval from minus infinity to 4. Right? We're going to consider solving this for x's in this interval, and we're going to also then consider solving it for x's in this interval. In this interval over here, we can remove the absolute values from the inequality because x minus 4 is greater than or equal to 0, so its absolute value is the number itself. And we then have x minus 4 less than 2x. Or, subtracting x, we have minus 4 less than x. So the numbers in here, which are larger than minus 4, are part of the solution set. That's all of the numbers, so we end up with the interval from 4 to infinity, like so, as being part of the solution set. Over here, when x minus 4 is less than 0, okay, then the absolute value of x minus 4 is its negative. So we can solve this then by replacing x minus 4 by its negative and removing the absolute value, and we then want to know when is this less than 2x, or when is minus x plus 4 less than 2x, or when is 4 less than 3x, so that's to say when x is larger than 4/3. Right? The numbers in here which are larger than 4/3 are the ones from 4/3 to 4, so we get 4/3 to 4, or 4/3 to infinity is the entire solution set, excluding the 4/3. Okay. One can work with more complicated inequalities by simply considering cases just as one was done before. Right? Let's consider a particular situation. Let's suppose we want to find when is absolute x plus absolute 2x minus 3 larger than 13. Right? Well, we've got several inequalities in here. We've got several absolute values in here, and we'd like to see them gone. Right? We can do this by considering several cases. X greater than 0 or equal to 0, and x less than 0 would be one case. Now, just as before here with inequalities, we can then, if we'd like to remove this one, we can consider two cases. 2x minus 3 greater than or equal to 0, and 2x minus 3 less than 0. Likewise, 2x minus 3 greater than or equal to 0, and 2x minus 3 less than 0. We now have four cases here, so to speak. What are the numbers in each case? Well, these are the numbers when x is greater than or equal to 0, and these are the numbers when 2x is greater than or equal to 3, or x is greater than or equal to 3 halves. So from 3 halves to infinity. This collection of numbers. Right? This is when x is greater than or equal to 0, and when x is less than 3 halves. So from 0 to 3 halves is this collection of numbers. These are the numbers when x is less than 0 and what? 2x is larger than or equal to 3, or x is larger than or equal to 3 halves. There aren't any such numbers. And these finally are the numbers when x is less than 0 and 2x is less than 3, or x is less than 3 halves. So these are the numbers from minus infinity to 0. So what we've done here then is we've broken down the numbers into 3 sets. The ones from minus infinity to 0, the ones from 0 to 3 halves, and the ones from 3 halves on to infinity. Right? Now, what we do with this is we work with each of these 3 sets. We consider these sets, these elements in here, and we find the solution set to this inequality. And since for these elements, both the quantities inside the absolute values are positive, we can throw the absolute values away, solve the linear inequality, and find out the solution to the linear inequality, and the numbers in here that are solutions to the linear inequality will be part of the solution set. Here, the same story holds, except that you remove the, x is greater than or equal to 0, so remove the absolute values here. 2x minus 3, however, is less than 0, so when you remove the absolute values, you have to replace this quantity by its negative, solve the resulting linear inequality, and find the solutions that are in this interval that are solutions to that resulting linear inequality. Over here, the same story. Both x is less than 0, though here, and 2x minus 3 is less than 0, so when you remove the absolute values around x here and the absolute values around here, you have to replace the quantity by its negative, and solve the resulting linear inequality. Let's take a look at this case right here. Right? Both the quantities are negative, so we replace x with minus x, replace absolute x with minus x. We replace 2x minus 3 with minus 2x plus 3, and we want to solve the inequality when is that larger than 13. That's to say, when is minus 3x larger than 10? That's when x is less than, dividing by minus 3 reverses the inequality, minus 10/3. Consequently, the numbers in here, which are less than minus 10/3, are part of the solution set. That's to say, part of the solution set is minus infinity to minus 10/3. The same type of argument has to be done with each of these 2 cases and the 3 pieces put together to get the entire solution set.